section 5.2, we're going to talk about properties of two things. Properties of rational exponents, which are just what types of exponents? Fraction exponents. And then also properties of radicals. So most of what we do, I think, is a review. And probably I think the part that most of my Algebra 2 students will struggle with are the radical portions. That's the backside. Okay, so kind of warm up with rational exponents. On that note at the top of your paper, I want you to write all previous exponent properties apply. So you already know some properties of exponents from Algebra 1. So when I talk about previous exponent properties, just as a quick review, I'm talking about things like this. Suppose I was doing x to the 4th times x to the 7th. You would tell me to do what? Sorry, what? Add your exponents. That would be x to the 11th. Or if I was doing something like x squared raised to the 5th, what should I do? Multiply my exponents, x to the 10th. And what's the other property that you know? If you're dividing, you subtract your exponents. So if I had x to the 5th over x squared, that would really be x cubed. Okay? So those things should sound familiar to you, and we're just applying them now to exponents that happen to be fractions. So that means I have to be able to add fractions, I have to be able to subtract fractions, and I've got to be able to multiply fractions. Other than that, I'm pretty much set. Now, before we get into those examples, do you see there's like a big space up there at the top? I want you to write x to the m over n. When we get to the back side, we'll be looking at the nth root of x to the m, essentially. But right now, we're looking at it in its rational exponent form, x to the m over n. And I just want to clarify, this whole thing is a power. So if you kind of look down at the different properties that we're going to be looking at, they're all in relation to like powers. Product of powers, quotient of powers, power of a power. So when we're talking about powers, we're talking about things that look like this, x to the m over n. Every power has a base. That could be a variable base or a number base. In this case, it's x. And every power also has an exponent. So back in Algebra 1, your exponents were whole numbers. Now in Algebra 2, in this section, our exponents are going to be fractions. So a lot of times people say stuff like, oh, x to the power of 2. Have you ever heard anyone say that? And you think x squared. Technically, it's x to an exponent of 2, and the power is x squared, all of it. It doesn't really bother me if you say to the power of, but for purposes of properties, make sure you know the power is the whole thing. Okay, let's look at the examples. The product of powers and the quotient of powers are very similar. When we talk about a product of powers, we now know powers are the bases and the exponents together, and a product implies what? Multiplication. So look at the two examples. You have two powers, 5 to the 2/3 and 5 to the 4/3, and you're multiplying them. You would tell me what are the rules for product of powers? You add your exponents. What do you do with the bases? You keep the base the same. You don't multiply 5 by 5. You just keep base 5. Okay? So let's write keep a base, add exponent. And for quotient of powers, we'll say keep the base, but subtract exponents. Now, I've left my first bullet point blank because I want to just make a quick note to you. In order for you to be able to use product of powers or quotient of powers, the powers must have the same base. So, like if you had something like x cubed y to the fourth, you can't add your exponents because you have an x and a y. Or if you had 5 squared times 3 cubed, you can't add your exponents because you don't have the same base. So for both of these, it's really important first that you have the same base. Then you can go through the work of keeping the base and adding or subtracting your exponents. Okay. See what you can do on A, B, on both of those. I'll give you a couple minutes. See what you can get done. Chat with your group members if you want.
Yeah, we're taking a shot in the dark, guys. So, that's the first one. It's going to be 5. This 6 over 3. And then 5.
Which one do you want?
I feel like that's going to be 25. So, like, let's simplify.
Yeah. Keep simplifying.
Okay, for the second one, I'm going to take another shot in the dark.
Which one do it, Charlie?
Like, 2.
Yes. Why don't you write that down?
Ooh, the second one is tough. Can't seem to figure it out. You just add them in. Here, let's go. Wait, what? What do you do? Are you in the first one?
Okay. I'm going to interrupt, so wherever you're at, just take a quick break. If I had 5 to the 2/3 plus 4/3, because I've got the same base, I'm going to add my exponents. That comes out to be 5 to the
Second.
6/3, which is 5 squared. Because it's my notes, I'm going to show all my work, right? Just so that anybody who's looking at it knows where I came up with it. And then that could be 25. Now, not always will they come out to be nice numbers that you could evaluate, but in the case that they do, go ahead and evaluate it. Nicely 25. When I do that second one, x to the 2/3 plus 1/3, what am I going to need to do in order to be able to add my exponents? Find common denominators. What's a good common denominator for 7 and 3?
21.
21. So multiply the first one by 3 and the second one by 7. So we'll get x to the 6 over 21 plus 7 over 21, and Aiden gives us x to the 13 over 21. Now, that one doesn't simplify in any kind of way. That's fine. Just leave it alone. It's a new power.
Rest.
All right, so over there in the quotient, we're just subtracting the exponents now. For letter A, what did you use for your exponent in the numerator? What is that? 3 to the 1. Right? If it's just a number, it's just being raised to the first power. It just is what it is. So that's 3 to the first. And then we should subtract our exponents. So 3 to the 1 minus 1/2 is just 3 to the 1/2. Now, TJ, you were saying 1 over 1 so that it looked like a fraction. But I I would argue on this one, you could probably subtract 1 minus 1/2 without having to get common denominators. So I'm going to do it the shortcut way. Are we okay with what I've done so far? Okay, tell me what you guys would do for B. Liam.
Well, make the bottom y the common denominator of 8.
Okay? So that would be y to the 3/8 over y to the 6/8. So get common denominators. And then what would you do? And how would you subtract them? Meaning? Okay, so you would subtract it top minus bottom. Okay, that's fine. So y to the 3/8 minus 6/8, which is y to the negative 3/8. And I like what you were saying there. You'll convert it at the end so that it doesn't have a negative exponent. So we talked about last week on Friday, negative exponents just flip what they touch, and we're going to write that down here in a little bit. That would be 1 over y to the 3/8. So I don't want your final answers to have negative exponents. That was probably true in Algebra 1, and that remains true here. So we're going to avoid the negative exponents. Now, I would argue that sometimes I can avoid that whole, extra work. If I see, when you got common denominators, and I ask myself, where are there more y's? 3/8 or 6/8. There's more y's in the denominator. So I am allowed to subtract bottom minus numerator, but then it stays in the denominator.
Oh.
So it would be 1 over y to the 6/8 minus 3/8, which is the answer that we got. Okay? Doing all right? Okay, moving right along. Power of a power. Okay, so it says power of a power. I just want to clarify. Remember, the power is the base raised to an exponent. So what it means is raise a power to an exponent. So now you've got an exponent outside your power. What would you tell an Algebra 1 student to do with their exponents? And I probably should write this on everyone, but it seems to happen more often with multiplying, so I'm going to write it down right now. That is, of course, simplify the exponent then if you can. A lot of times when you multiply, you might be able to reduce at the same time. So go ahead and take care of that. I like to do my reducing as I'm multiplying through cross-canceling. So if there's anything in a numerator that cancels with a denominator, I can go ahead and cancel that out. So for the first one, 7 to the 2/3 times 5/2, the 2's will cancel. 2 in the numerator will cancel with 2 in the denominator. And that will leave me with 7 to the 5/3. Now, you don't have to cross-cancel if you don't want to. If you want to just multiply across, you guys should be listening. If you just want to multiply across on top and multiply across on bottom and simplify later, you can do that. 2 times 5 is 10, 3 times 2 is 6, 10 6 is 5/3. So it doesn't matter which way you do it, you'll get the same answer. I just threw B in there just for fun. It's not really a rational exponent because it's irrational. It's a square root of 3. It's not a fraction. But the property still applies. What would you do with the square root of 3? Multiply square root of 3 times square root of 3, which is?
3.
So again, the properties of exponents don't change just because the numbers look weird. Fractions, radicals, whatever. Keep doing the same thing you would normally do. Now, I decided just to close out with your other properties of exponents just because now is a good time to review them. So let's all recall what's true about anything raised to 0. It's equal to 1. Get a lot of zeros on that answer every time. Anything multiplied by 0 is 0. Anything raised to the 0 is 1. So in this example, of course, it's a product of powers. I would add my exponents. 1/5 plus negative 1/5 is 0, so z to the 0 is just equal to 1. We talked about this on Friday. What's true about the negative exponent property? Flips what it touches. And what else could we add to that? Doesn't make it negative. Thank you. Flips what it touches. Does not make it negative. I like to say flips what it touches. It's not really like super precise language here, but it just tells me like if it's in the numerator with the negative exponent, it goes to the denominator. If it's in the denominator, then it goes to the numerator. Okay, just flip flops. A is like what we did on Friday. It's just a good review of simplifying expressions with rational exponents. So this negative exponent would flip. The 8 to the 1/3 would show up in a denominator. Once you make the flip, it becomes positive. So it's no longer a negative exponent. And then 8 to the 1/3 is really 1 over 2, or 8 to the 1/3 is 2 because it's the cube root of 8. So 1 over the cube root of 8 is 1 over 2. Some of us might be able to go right from rational exponents to 1 over 2. Some of us may still need to write the radical out. Okay, some of us will use that path. I don't know. I'm going to do it on board. And then in B, I just wanted to make a point here that the negative exponent only flips what it touches. So like x to the 4/3 does not have a negative exponent. It should not flip. Z to the 1/4 should move to the bottom, and y to the 2/3 should move to the top. So x to the 4/3, y to the 2/3, and z to the 1/4. Here's your answer. Did you get that, Aiden? And they're all different bases, so there's really nothing else for me to do. Okay, so give me thumbs up, thumbs to the side, thumbs down. How we feel about properties of rational exponents. Okay, I'm getting mostly this. Okay, some of us who tend to just sort of like freak out when we see fractions need to really focus on our practice, right? Like, you gotta stay calm. It's just adding, subtracting, or multiplying. No rules have changed. Okay, now here's where things can sometimes get a little bit messier for us.
That's nice.
Oh boy. It's not too bad, but it just gets to be a lot. Now, I would argue that you probably have already learned the product and quotient rules for radicals. Okay. We actually use product rule a lot when we're simplifying radicals, so I'll show that to you as well. Here are our product and quotient rules. We're used to seeing square roots, but since we're in chapter 5 and we're in algebra 2, I'm going to call them nth roots. Okay. So the nth root of A times the nth root of B can also be written as the nth root of A times B. And this property works both ways. So I can have two separate radicals that have the same root and make them 1 through multiplication, or I could have one radical and separate it and then work it out. So this is actually the property we use to do things like the square root of 72. When I say like write it in its simplest radical form, we look for perfect squares that are factors of 72. So the biggest perfect square that's a factor of 72 is 36. So that's 36 times 2. And then essentially we break it up. It's the square root of 36 times the square root of the square root of 36 times the square root of 2, which is 6 square root of 2. So we've been using that property for a long time, breaking it up. And you can use that same property for like cube roots and fourth roots. Okay. So if I was doing like a fourth root of 32, if you look at your table in your notes that we created last week on Friday, and you look in the fourth column, 32 isn't in it, but 16 is. So that could be the fourth root of 16 times 2, which is the fourth root of 16 times the fourth root of 2, which is 2 fourth root 16, or sorry, fourth root 2. And it just keeps working for all the other roots. So you're going to want to spend some time with that table in your notes from Friday as well. Like you want to get more familiar with some of the smaller roots, okay, in each of the columns. Okay, and then quotient is almost exactly alike, except instead of multiplication, it's division. So you're going to have an nth root of A divided by an nth root of B, and you could put that underneath 1 nth root. And you can break it up or you can put it together, whatever is going to work for you. Now, I will put one little reminder here. In the properties of rational exponents, you always have to have the same base. In the properties of radicals, they always have to be the same root. So, like, you could only do that if it's a cube root with another cube root. If you were taking a cube root times the square root, no can do. Okay, so let's look at our examples. Letter A is pretty straightforward. That's going to be the cube root of 8, which is 2. If you can simplify it, do. In B, I'm going to do the cube root of x squared times x to the 4th, which is really x to the 6. Yeah, jumping ahead there. But then can you do the cube root of x to the 6? Yes, it's x squared. And we're going to talk more about that down below when we do the remainder piece. Okay, but there's a different way. Like you could think about that as its rational exponent. The root is in the denominator, so that's x to the 6/3, which is x squared. Okay. C, I will say this. There's more than one way to do C. Like I could work to try to simplify the fourth root of 240. Like, is there a perfect fourth that goes into 240? Can I simplify it? If so, I could work around that way. But since 240 is not a perfect fourth, what I might try to do is use my property of radical and put them underneath together. Can someone tell me what 240 divided by 15 is? 16, and the fourth root of 16 is 2. So I would have been able to simplify the fourth root of 240, and it would have canceled out with the fourth root of 15 below to leave us with just 2. Okay, but it's probably faster to divide them first in that case. Okay, what's weird or different about D and E?
Different.
Okay, they're not in radical form anymore, right? These look like rational exponents, the first side of our notes. Okay, what's the trouble with trying to do D or E with rational exponents? They don't have the same base. So if I go back, like I cannot add the exponents because I have 2 different bases, and I can't subtract the exponent because I have 2 different bases. So sometimes when you get to something like this where it looks like rational exponents but the property don't apply, try rewriting it the other way. 3 to the 1/4 is really the fourth root of 3. And 4 to the 1/4 is really the fourth root of 4. And now as radicals, I can see very clearly they have the same root. So then I can make it the fourth root of 12. Liam, did you have a question?
Would it be
Oh, you could do 12 to the 1/4. Yeah, I'm gonna say most people like that becomes like too much. Like now you got rules for exponents and rules for radicals, and then rules with different big. Like for a lot of people, it's like let's just have rules for radicals and rules for exponents, and if it doesn't work, try to change. But yeah, I mean it is 12 to the 1/4. That's fine. And then this one works the same way. It's the square root of 12 over the square root of 3. So that's the square root of 12 over 3, which is the square root of 4, which is 2. But, ma'am, if you saw that and you recognize it, if you could do 4 to the 1/2 and then call it 2, that's fine with me. You can keep all that straight, that's great. Okay, questions, concerns from the people. Okay, so over to the side I thought, well, now is also a great time to review adding and subtracting radicals if we're going to be working with radicals. And the thing that I would say to you about adding and subtracting in any math class with any teacher in any grade is always the same. Never does addition or subtraction ever change. Addition and subtraction is always combining like terms. It's the only thing you do when you add and subtract. We just did it with polynomials. Added and subtracted like terms. We did it when we did complex numbers with I. We added and subtracted like terms. Okay? So I'm going to put that as one of my bullet points. Adding and subtracting radicals is combining like terms. And in radicals, like terms means it has the same root and the same radicand, which remember the radicand is the thing underneath the radical. So I always tell a little story about adding and subtracting radicals just for some people who sometimes it doesn't click right away. And my story is, imagine a Walmart where you could shop for radicals. How awesome. Every aisle was a new kind of radical. Like there's an aisle for square roots of 2, and there's an aisle for cube roots of 4, and there's an aisle for square roots of 5. And you just go shop for whatever radical you need. So you got your little cart, and you're going down the aisle, and you're like, oh my gosh, cube roots of 2. I always need cube roots of 2. So I'm going to put 5 cube roots of 2 into my cart. And I keep shopping, but before I leave that aisle, I'm like, you know what? I always need cube roots of 2. Let me put 2 more cube roots of 2 in my cart. How many cube roots of 2 are in my cart? 7. Thank you for listening to my story. So they're just things that we add. When I put them in my cart, they don't turn into cube roots of 4 or 6 roots of 4 or anything like that. They're all just cube roots of 2 things, right? And I can add up how many cube roots of 2 I have. Now, if I put in a cube root of 4, that's something else that will tally up separately on my receipt.
It's like if you're buying cereal or a bag of salami. There are 2 different things.
Yes, very true. Okay, 2 different aisles for sure. Okay, so letter A. Can you add 2 cube roots of 3 plus a cube root of 3?
Yes.
How many do you have?
2. Wait.
3.
3.
I have 3 cube roots of 3. They don't turn into cube roots of 6 or anything like that. There's no adding with the roots or the radicands. You're just adding like what I would call the coefficients to the radicals.
That's a lot of 3's.
Yeah, it is. Okay, B would be 4
Wait, no,
square roots of x. Okay. C, 11 x to the 2/3. I mean, aren't rational exponents essentially the same thing as radicals? So I could only combine like terms. And addition and subtraction is always the same no matter what it looks like. Combine like terms. D.
3 to the 3rd radical. 3 to the 3rd, and then it's gonna be 5th in the radical. Can I say why I got that?
Yeah.
Okay,
I'm
so
confused.
you're gonna break that up to 40 to 8 and 5, And you know 8's a perfect cube, so it's going to be 2 on the outside.
Okay, so he's simplifying. Right now, can you add them?
No.
Not like terms. Nope. Not gonna add them. But check them. See if you can simplify it. The cube root of 40 could really be written as the cube root of 8 times 5. 8 is a perfect cube, right?
Yeah.
So then that's 2 cube roots of 5 plus a cube root of 5, which is 3 cube root of 5. Say that, TJ. 3 cube roots of 5.
3 cube roots of 5.
Okay.
Yeah, speaking of
Questions, concerns? Okay? Alright, so remember, addition and subtraction is always the same. Add or subtract like terms. Okay, now the next part, we can do it long ways or we can do it short ways, and my goal eventually is to do it short way, right? Because I want to do the least amount of work. But I'll do a couple the longer way so that people can kind of see where this is coming from. My shortcut is what you're seeing up at the top. Like do m divided by n and then put the remainder inside. Okay, but that may not make total sense to us right now. So we're going to start with a, which is a cube root of x to the 5th. Now this one's kind of like the cube root of 40. We didn't know the cube root of 40 right away. It's not on the list of perfect cubes, but TJ was able to spot 8 is a perfect cube inside of 40, a factor. So when I look at x to the 5th, are there any perfect cubes inside of x to the 5th?
Yes.
What is it?
X cubed.
X cubed is a perfect cube because it's x times x times x and its root is x. So I could rewrite this really as the cube root of x cubed times x squared. Do you agree that that is the cube root of x to the 5th? Okay. And then do the cube root of the perfect cubes. So the cube root of x cubed is x, and then I'll have times cube root x squared. There's not enough x's there for me to be able to do that cube root nicely. And if you think about this one as a rational exponent, isn't this x to the 2/3? It's not quite 1. It doesn't have enough to be a whole x, so it's stuck in underneath. That's my answer. Okay, I'm going to look at B. Now, the cube root of 256, or sorry, it's the fourth root. The fourth root of 256. Do you know the fourth root of 256? It is 4. It's on our list. It's a perfect 4. Okay. So that one's good. I don't have to break it up, right? If it wasn't, I would try to look for a perfect fourth factor, like we did with 40, 8 and 5 for the perfect cube. Okay, so I'm going to leave it alone. X to the 6 is not a perfect fourth because 6 divided by 4 doesn't divide nicely. Is there a perfect fourth inside of x to the 6th? X to the 4th, because then it will divide nicely. So we're going to say x to the 4th and x squared. And then y to the 7th I can write as y to the 1st, y to the 4th, and y cubed. I'm again looking for perfect fourths, right? Basically, like with the radical or with the variables underneath the radicals, you want your exponent to be a multiple of the root. So like a multiple of 4. And then you can go through and you can clean up all the ones that are perfect. So we said the fourth root of 256 was 4. The fourth root of x to the 4th is x. And the fourth root of y to the 4th is y. The x squared and the y cubes don't have enough to come out, so they got to stay underneath. So fourth root of x squared y cubed. Okay, now this leads me to my shortcut, because I don't want to write that down every time, but if you like to, you can. When I take 6 divided by 4, how many times does 4 go into 6? Once. So I can take out x to the 1st, That's really x to the first right there. And then the remainder of 6 divided by 4 is 2. So the remainder gets stuck inside x squared. And the same thing happens with y to the 7. 7 divided by 4 will go in nicely once, so I can take out a y to the first, and then I'll be left with the remainder of 3, so y cubed is underneath. So I'm going to use my shortcut for the next one. Okay. Cube root of 24. Do you know that one right offhand? No, because it's not on the list. Are there any perfect cube factors of 24?
8.
8 and 3. Okay. So, I can do the cube root of 8, that's 2. The cube root of 3 is going to stay underneath. And then I just do my letters one at a time. I'm going to start with the x's. This would be 6 divided by 3. 2, remainder is 0, so I don't need to put an x underneath. Then I'm going to do y to the 5th. 5 divided by 3. Can get it in one time, so it's going to be y to the first outside. Remainder is 2, so y squared remains. And then z squared, 2 divided by 3, not enough. So no z's can come out, z squared stays underneath. It's really, I think it's really handy to just kind of go one at a time. I'm not going to make it look really terrible by looking at them all at once. I'm only going to focus on one letter. Which then leads me to D. D is a subtraction problem, but right now they don't look like terms. Over there in D, I can't subtract 3x cube root of x from a cube root of 8x to the 4th. Those are totally different, but I can try to simplify cube root of 8x to the 4th. Cube root of 8x to the 4th is 2x cube root x. And then I have 3x cube root x in front. Can I subtract those? Yeah, those are exactly like terms. They are x cube root x terms. I have 3 minus 2, so I really have 1. X cube root x. I'm just subtracting the coefficients. Okay. Questions, concerns? Okay, last thing we want to talk about is rationalizing that denominator. Rationalizing the denominator is turning the denominator into a rational number. A number that could be written as a fraction. Generally, it's just a really nice number like a whole number. So we do this because there are no radicals, which are irrational, allowed in the denominator. Now we had practiced this back in chapter 3 when we were solving quadratics. Things are going to be a little bit different now that we have not just square roots, but nth roots. So we're going to try to think through what changes when they become different. Yep. So this one, the cube root of x over 5, we can't leave it like that. We've got to break it up. It's really the cube root of x over the cube root of 5. And I don't want to leave it like that because I want to rationalize my denominator. So what would you tell me like normally to do to rationalize my denominator? Multiply by a cube root of 5. Okay. So back in quadratics, we would just multiply by whatever was in the denominator, right? And that was great for square roots, because a square root times a square root is the thing underneath. But this is a cube root times a cube root. A cube root of 5 times a cube root of 5 is really the cube root of 5 squared, or 25, and we don't know the cube root of 25. How many cube roots do you need to make 5? Cube roots.
2.
2 would be for square roots. Cube roots need 3. How many do you have right here? 2. You need another one. Now, a cube root of 5 times a cube root of 5 squared is a cube root of 5 cubed, which is just 5. And then up in the top, those are both cube roots. I can just multiply the stuff underneath them. That's going to be x times 5 squared. So the cube root of 25x. Okay, let's try one more to see if we can get the hang of this. 5th root of 32 over y. This is the 5th root of 32 over the 5th root of y. Well, the 5th root of 32 is really 2. We're not allowed to leave that 5th root of y in the denominator.
So in the previous, when you have the cube root of 25x over 5, why wouldn't you just take out the 5? Would you have to? Is that because you would need to take it out from everything above the bar?
What do you mean take out the 5?
Take it from out of 25.
You can't reduce if it's underneath the radical in one and not underneath the radical in another. Okay, what would we multiply by? Start with. I'm not going to be able to hand out your test if you guys don't answer me. The 5th root of y. Okay, that only gets me to the 5th root of y squared. How many 5th roots of y will I need? I'm going to need 4 because I got to get to 5 of them. So that leaves me with 2 5th roots of y to the 4th all over y. Now remember we talked about, like, I don't care if this 4 is outside the radical or inside the radical. It's all the same when we're rewriting it as x to the m over n. So either way is fine. Questions for me? PJ, can you pass out the homework assignment?
Yeah, I got you.
Yep.
I missed it. What's the note thing at the very top of it?
No radicals